Now we'll continue with exercise 1.1, question number 2, which says that R is a relation defined on the set R of real numbers, and R is defined as A comma B such that A is less than equal to B square. The question says we need to prove that this is neither reflexive nor symmetric nor transitive. Whenever we need to prove that it is not reflexive, that means we need to give an example. Not symmetric, give an example. Not transitive, give an example. So for the reflexive part, we have to think of an example where A comma A does not satisfy this condition. We have to think of a number whose doublet does not satisfy this condition, which is A less than equal to A square. If we think of any natural number, whole number, integer, the number is always less than its square, like 2. 2 is always less than 4. 3 is always less than 9. So a number, an integer will always be less than its square. So what can be a real number which is less than its square? For that, we have to consider fractions. So we will write, consider half comma half. Now we need to compare half with the square of half. Square of half is 1 by 4. Now we know that 2 is less than 4. And if we take the reciprocal, then 1 by 2 is greater than 1 by 4. This implies half is greater than half ka square. So we can say that half comma half does not belong to R, and therefore the relation R is not reflexive. Now we'll move to the symmetric part. Now since we need to prove that this relation is not symmetric, so we need to prove that A comma B belongs to R, but B comma A does not belong to R. So we will write, consider 1 comma 2. First of all, we'll show that 1 comma 2 belongs to R. How? 1 is less than 2 ka square, which is 4. This implies 1 comma 2 satisfy the condition of the given relation, and therefore 1 comma 2 belong to R. But if we consider B comma A, which is 2 comma 1, 2 is greater than 1 ka square. This implies 2 comma 1 does not satisfy the relation, the equation of the relation, and therefore we can say 2 comma 1 does not belong to R, and therefore the relation is not symmetric. Now we need to talk about the transitivity. For transitivity, we have to find the numbers A comma B, B comma C, such that both of them belong to R, but A comma C does not belong to R. Because in the question, we have been asked to prove that this is not transitive. We have to think of example. If we take this example as 3 comma 2 and 2 comma 3 by 2, I'll take this as AB and this as BC. Now what I will prove is that A comma B belongs to R. I'll prove that B comma C also belongs to R, but A comma C does not belong to R. So first of all, we'll consider A comma B, which is 3 comma 2. Now 3 is less than the square of 2. This implies 3 is less than 4. So we can say 3 comma 2 belongs to R. Now we'll come to B comma C. B comma C is 2 comma 3 by 2. 2, we need to compare it with the square of 3 by 2, which is 9 by 4. Now 9 by 4 will give me 2.25. So I can simply say 2 is less than 2.25. This implies 2 comma 3 by 2 also belong to R. But if we consider A comma C is 3 comma 3 by 2. I need to compare 3 with the square of 3 by 2, which we have calculated as 2.25. And I can clearly say that 3 is greater than 2.25. So we can say that 3 comma 3 by 2 does not belong to R. And therefore, we have given an example where A comma B belongs to R, B comma C belongs to R, but A comma C does not belong to R. And therefore, we can say that the relation R is not transitive. So the relation R is not. Now we'll move to question number 3. Now question number 3 says Check whether the relation R defined in the set 1, 2, 3, 4, 5, 6. So if I take this set as A, it means our relation is defined from A to A. That means all the X can take their value from A and all the Y also can take their values from A. The relation R is defined as A comma B such that B is equal to A plus 1. We need to check whether this is an equivalence relation or not. First of all, we'll write R in roster form. X can pick the values from here, Y can also pick the values from here. If we take X as, or we can say if we take A as 1, the value of B will be 2, A as 2, value of B is 3, 3 comma 4, 4 comma 5, and 5 comma 6. That's it, because if we take A as 6, our B will be 7, which does not belong to the set A. So this is our relation. First of all, we'll check for reflexive. Now for reflexive, I've already told you that reflexive means that all the elements which are there in the set A, the doublet should also be present in the relation. We can clearly see that 1, 1, 2, 2, 3, 3, neither of them belongs to R. So we have to give an example. So we'll write 1, comma 1 does not belong to R. Therefore, R is not reflexive. Next, we'll move to symmetric. Symmetric, maybe we will check all the elements. Now I can clearly see 1 comma 2 belongs to R, but 2 comma 1 does not belongs to R. Therefore, the relation is not symmetric. And now we'll move to the last part, which is transitive. For transitive, we need to search for A comma B and B comma C. So 1 comma 2 is there and 2 comma 3 is there. 1 comma 2 and 2 comma 3, both of them belong to R, but I can see that 1 comma 3 does not belong to R. Therefore, the given relation R is not transitive. Now we'll move to the next question, question number 4. Question number 4 is, the relation R is defined on the set R of real numbers. It means R is defined from R to R. That means all the A are real numbers, all the B are real numbers. The relation is defined as R is equal to A comma B such that A is less than or equal to B, and we need to check, or no, we need to show the relation is reflexive and symmetric, but it is not transitive. So we need to show the relation is reflexive. We know that the number is always equal to itself. So we can say, consider a real number A. A is always equal to A. It means this condition is satisfied. It should either be less than or it should be equal to. The number is equal to the number itself. This implies A comma A belongs to R for all A which are real numbers. Now we move to symmetric. In the question, it is given that we need to prove that it is not symmetric. So we'll give an example. We will write consider 1 comma 2. Now we know that 1 is less than 2. This implies 1 comma 2 belongs to R. But if we take 2 comma 1, 2 is greater than 1. That implies 2 comma 1 does not belongs to R, and therefore relation R is not symmetric. Now for transitivity, we need to prove that this is transitive. That is, if we take A comma B, B comma C belongs to R, we need to show that A comma C also belong to R. In the question, we have been asked to prove that this is transitive. So we'll write, let A comma B and B comma C belongs to R. Now A comma B belongs to R. This simply implies A is less than equal to B. In the similar way, B comma C belongs to R implies B is less than equal to C. B comma C belongs to R implies B is less than equal to C. Now I can clearly see A is less than equal to B, B is less than equal to C, and this simply means A is less than equal to C. Therefore, A comma C belongs to R, and therefore the relation R is transitive. So we have proved that the given relation is reflexive, it is not symmetric. This we have proved by giving an example, and it is transitive. Whenever we need to prove something, we need to prove it using the definition, and whenever we need to disprove something, we need to give an example. Now we'll move to question number 5. Question number 5 says check whether the relation R defined on the set R of real numbers, it is defined as R is equal to A comma B such that A is less than equal to B cube. We need to check whether the relation is reflexive, symmetric, or transitive or not. Now for reflexive, what we need to find out is we need to find out a number which is less than its cube. Just like I explained in question number 2, that a number is always less than its square. In the similar way, a natural number, a whole number, an integer is always less than its cube. But if we talk about fractions, then they are greater than their squares, they are greater than their cubes. So we will write, consider half comma half. Now we need to compare half with the cube of half. The cube of half is 1 by 8. We know that 2 is less than 8. This implies that half is greater than 1 by 8. Means we have found out a number which is greater than its cube, and therefore we can say that half comma half does not belongs to R, and therefore the relation R is not reflexive. Now we need to look at the symmetric part. For symmetric, we have to take an example in which A comma B belongs to R, but B comma A does not belong to R. So we'll think of an example. We'll take the same example which we took in the last question. We'll take the example 1 comma 2. So for the symmetric part, we'll take the example 1 comma 2. 1 is less than the cube of 2, which is 8. So 1 comma 2 belongs to R. But if we consider 2 comma 1, 2 is greater than the cube of 1. This implies 2 comma 1 does not belong to R, and therefore we can say that the relation R is not symmetric. And lastly, we'll move to transitivity. For transitivity, we need to show that A comma B belongs to R, B comma C belongs to R, but A comma C does not belong to R. For transitivity, we'll take the example in such a way that A comma B and B comma C belong to R, but A comma C does not belong to R. So we have to think of an example like that. For transitivity, we will take an example. Let us consider the example 3 comma 2. Let us take the example 10 comma 3 and 3 comma 2. So this is A, B, and this is B, C. So if we look at A comma B, 10 is less than the cube of 3, which is 27. 3 is less than the cube of 2, which is 8. So this simply implies that 10 comma 3 and 3 comma 2 both belong to R. But if we look at A comma C, which is 10 comma 2, we have to compare 10 with the cube of 2, which is 8. And I can clearly say that 10 is greater than the cube of 2. So 10 comma 2 does not belong to R, and therefore we can say that the relation is not transitive. So this relation is not transitive.